Hello, my name is Dr. Jonathan Butsky. I'm not a medical doctor. Instead, I'm a robot doctor. Have you ever seen a real-life robot? What do you picture when you think of one? Does it have arms and legs? Or wheels and funny tools for hands? What is the purpose of the robot you have in your mind? Our mission is simple. In this introduction, we're going to explore how robots solve the problems that allow them to be useful in the world. We'll do this with nothing more than the math concepts you may already know: geometry, trigonometry, basic algebra, and a few concepts from physics. We'll even help you brush up as we go, but be prepared to take notes. In this episode, we'll talk about the purpose of robots. What are they used for? How does that purpose affect some of their design elements? We'll look at examples of different robots and see how they're used in different industries, some of which you might not expect.
They're not just in movies anymore. Robots are now the ideal candidates for taking over dirty, dangerous, and dull jobs. They're a vital part of many industries. You'll find them in manufacturing plants, moving heavy objects with great precision, or tightening engine bolts to exact specifications. In agriculture, a robot can monitor crops or take on tedious jobs around the farm. They're often used to keep people out of harm's way. Civil engineering companies might need a robot to inspect dams or bridges. Robots can also apply paint in automobile factories to keep humans away from dangerous fumes. In the military, a robot can find buried explosives, keeping soldiers and civilians safe. Doctors rely on robots when they perform complex surgeries, or you might see a robot delivering medicine and clean sheets, so the hospital staff can spend more time with their patients.
They can do a lot, but of course, robots don't have a brain. They rely on humans to tell them how to solve problems. They have a lot of problems to solve. How do robots know where they are? How do they move from one spot to another? How do their sensors work? How do they know what to do next? All these problems can be solved with basic concepts from geometry, trigonometry, and algebra. We can use trigonometry and geometry to determine where a robot is, given the distance to a few surrounding objects. Throw in some algebra and we can use two cameras looking at one object to determine how far away it is. Finally, we can keep track of where the robot has moved by using concepts from physics and math. Here's a general roadmap of our class. I'll point out the key concepts for you to learn. To help with that, we'll work through some example problems, and then I'll give you a few challenge questions to work out on your own. Remember, you'll need to take notes. Today's topic: what purpose does a robot have, and how does that purpose affect its design? How does the robot move? How does it interact with the environment? And what does it look like? We can customize robots to make them faster, more efficient, or better at their assigned tasks. So let's talk about some of these design elements. We'll look at locomotion, how a robot moves through its environment. You'll need to consider the robot's end-effectors, basically its hands and tools. Modify them to get the best performance. Appearance is important too. Change the way it looks so it can better fit in and get the job done. What you want the robot to do will drive these design elements. Let's first look at locomotion, how a robot moves.
There are legs, wheels, and robots that fly, and plenty of robots are simply bolted to the floor. Why would you choose one of these options? What are the benefits of legs over wheels, for example? The answer is in the robot's environment. Wheels do well on hard surfaces. They're efficient and quick. That's why cars and trains use wheels. But wheels can get stuck in rough terrain, or sand or mud. That's when a robot designer might want to use tracks instead. If the robot needs to move off-road, then tracks might solve the problem. Essentially, tracks give the robot its own smooth road surface under its wheels, working better on soft or bumpy surfaces. But for very uneven terrain, tracks suffer the same fate as wheeled robots. That's where legs come in. Legs use more energy than wheels or tracks, but they are adaptable to all sorts of terrain. You can climb over objects or stand on them. NASA has even developed legged robots that can explore volcanoes. But what about even more difficult situations? What if you need to inspect the underside of a bridge or check the roof of a tall building? Well, your robot might have to get off the ground to do its job. Flying robots can go more places and get there much faster, but there is a downside. A flying robot needs more energy to stay in the air and much more energy than a ground robot needs to stay on the ground. Flying robots have to be as light as possible to maximize flight time, and that limits the types of tools and sensors these robots can carry, which will also limit the types of jobs they're good at. One more option: robots that don't move at all. Factory robots just sit in one place and have their work brought to them. The robot can move its tools and arms, but its base is bolted to the floor. Automotive assembly line robots and other industrial robots are among the most common robots in the world.
When it comes to locomotion, you've seen the pros and cons. Wheels, good because they're fast and energy efficient, but they're only useful on smooth terrain. Tracks, better on rough terrain and still fast enough, but they're less energy efficient than wheels and not as capable as legs. Being able to walk can get a robot through the roughest terrain, but legged robots are slow and use a lot of energy. The pros of a flying robot: it can avoid terrain altogether, and it's fast, but it uses the most energy and it can't carry a heavy load. The stationary robot is cheaper and doesn't use much energy at all, but they're less flexible and limited in what they can do. Our second design element we call end-effectors. What's at the end of the robot's arm, and what effect does it have on the environment around it? Does the robot have a hand or a built-in tool? If it has a hand, is it a simple gripper, or does it have fingers like a human? End-effectors can be a wide variety of tools, from grasping hands to paint sprayers and welders. If the robot is working with humans, it probably needs a human-like hand in order to use human tools. On the other hand, if the robot is operating by itself, it can have specialized end-effectors that are specific for its job. Like in a coal mine, the robot might need a drill or a scooper. If the robot only needs to perform basic grasping, a simple 2- or 3-fingered gripper should do just fine, able to pick up many objects. But they lack the fine dexterity of a multi-fingered hand. They probably won't be able to thread a needle or put in a screw. A gripper with 5 fingers is much more like a human hand and can use human tools without modification. That's much better for fine dexterity work, but it comes at a cost. Compared to a 2-fingered gripper, the 5-fingered hand is more expensive and harder to program. Some robots need to grasp objects gently. That's when a robot might use deformable bags instead of using a gripper at all. The robot places the bag on the object and sucks all the air out so that it conforms to the object's shape, cradling it softly. When it's time to set the object down, the robot releases the vacuum and the bag returns to its normal shape, leaving the object safely behind. Perfect for delicate items like eggs or light bulbs. Another option: suction cups. Picking up items with an intake of air, then setting them down by releasing the vacuum. Good for things that are smooth and flat, like these small items, or even a large plate of glass. Instead of hands, some robots have tools built right into their arms. You might see this all the way down an assembly line. At the beginning, the robot has a welder to put pieces of metal together. Later, torque wrenches to install engine components. And finally, a paint gun to apply a nice even coat of color. Other robots may not have end-effectors at all. A flying robot moves through space, positioning itself to perform tasks, like inspections, with its camera or sensor. Selecting the manner of locomotion and the type of end-effectors impacts what the robot will look like. That's our third design element: appearance. If your robot has to work around people and act in a human-like way, well, Your robot might look something like this.
One example is the Robonaut. It was designed for NASA to work alongside the astronauts in the International Space Station. The Robonaut was able to move around like a person and use the same tools used by the real astronauts, saving NASA time and money. Human-like robots aren't the only ones that have to fit in. Robotic vehicles tend to look an awful lot like the vehicles they're replacing. Self-driving cars look more or less like regular cars, maybe without the steering wheel. And flying robots usually look like real helicopters.
Let's look a little deeper at other industries that use robots, like the medical field. In hospitals, robotic tugs move supplies and medicine from supply areas out to the nurses' stations. That saves humans from having to make the trips back and forth. For this to work, staff members put in a request for a particular item. The central receiving location loads those items onto the robot, which automatically goes to the right floor. Robots also work outdoors. They can help farmers by monitoring their crops, looking for areas that need more water, fertilizer, or pesticides. Better precision means using fewer pesticides and fertilizer, saving the farmers money, and reducing the impact on the environment. Indoors, you might see robots in warehouses, moving goods back and forth between shelving, packing, and shipping areas. In retail stores, robots can patrol the aisles, checking the inventory. If an item is low, the robot automatically places an order for new merchandise. In this episode, we covered the reasons behind a robot's locomotion, end-effectors, and overall appearance. All three of these design elements are driven by the jobs the robot needs to do. And for each design element, you now know the pros and cons. Now, for your assignment and these challenge questions. For these questions, think about what kind of design decisions would need to be made for a particular task. For example, a robot operating in Antarctica may have tracks to drive over the snow, while a robot used in your house would need an end effector capable of opening doors. Choose a task for your robot, whether it's working on the farm, say collecting strawberries, or working on a construction site, excavating ground for a basement, or even a job around your home. Choose your design elements. What does your robot need to get its job done? Then explain how those design elements help the robot to perform its job. Finally, do the same steps for a different task and describe why the two tasks result in different design elements in different robots. Again, to recap your assignment, choose a task, choose your design elements, explain them, then choose a different task and compare. I'm John the Robot Doctor. See you next time.
You can find these video lessons online at WQED.org/therobotdoctor.